We have worked on ordinary differential equations. We've worked on partial differential equations for the last few classes. I want to wrap up solving numerically differential equations with one class on coupled differential equations. So just to be clear, in partial differential equations, there are differentials with respect to more than one independent variable. Maybe it's the position coordinate x, the position coordinate y in the Laplace equation, or maybe it was the position coordinate x and time t in the diffusion equation. But you got differentials with respect to more than one independent variables. In the coupled differential equations, we got differentials with respect to one independent variable. In today's class, that independent variable is going to be time, but we've got more than one function of that independent variable. We've got more than one coupled with more than one differential equation that are coupled through that more than one independent function of the dependent variable. So that's what a coupled differential equation is. I mean, maybe you already knew it. I've just made it less clear, or maybe it's clearer now. I don't know. An example of the problem that we're going to solve today would be a molecule, say a carbon dioxide molecule. It's an arrangement of one carbon atom and two oxygen atoms that are bound together. And it's like three masses, three atoms or ions on springs, connected by two springs. And so this is a coupled system of three masses through two interactions, two springs. And that can be described by coupled ordinary differential equations and solved by solving coupled ordinary differential equations. If you have one mass on one spring, then that system has a natural mode of vibration, a natural frequency, a natural period. If you have multiple masses that are connected together by springs, then you will have more than one natural vibration mode, more than one natural frequency, natural period. And that's the type of problem we're going to solve today. Specifically, we're going to look at a problem that our problem will involve two masses and three springs. The homework problem will involve three masses and four springs. But for our in-class problem, two masses, two springs, we're going to describe that with coupled differential equations. And then we're going to solve those coupled differential equations. We'll look at the analytical solution, what we can learn from that. We'll compare it with the numerical solution. And explore that. So that's the goal. Okay. Here's the problem. So upstairs in the figure, I've got in purple, I've got two masses, two blocks. They are connected with springs. There's a spring on the left that connects to the wall on the left. There's a spring on the right that connects to the wall on the right, so the walls are fixed. There's a spring in between the two masses that connects together the two masses. And so this system is going to be described by a pair of coupled differential equations. I've given names to the various quantities that are involved in the problem. So we've got two masses, M1 and M2. We've got three springs, K1, K2, K3. The independent variable is time. So we're going to watch the positions of the masses over time. The dependent variables are the position of the left-hand mass, called it x1, position of the right-hand mass, called it x2. And that's what we want to figure out. That's what we want to solve for, and we're going to do it a bit analytically, and then we'll do it numerically. We can imagine what's going to happen in this arrangement, right? If you stretch the spring on the far left the one that's attached to the wall, that's going to directly exert a force on the mass on the left. And it will, if we stretch that spring on the left, it's going to pull that mass towards the left. If we compress the spring on the right, so the one that's attached to the right-hand wall, and compressing that spring will create a force that's directly applied to the second mass, the right-hand mass, and then that'll be towards the, if we're compressing that spring, that'll be towards the left. On the other hand, for the spring in between the two masses, then if we compress that spring or stretch that spring, that's going to create forces that are equal and opposite on the two masses on either that are attached to it. So that is the coupling between the motion of the mass on the left and the motion on the right is through that spring in the middle that are called KE. Okay, so we're going to set up a pair of differential equations, ordinary differential equations for the two masses, two equations for the two masses, and we're going to solve for the position as a function of time x1 and the position 2 as a function of time x2 of the two masses. So this is a problem that you've probably met before. It's like a classic problem, so some sort of initiation thing. And we'll just work through it kind of quickly. So I'm assuming that you've sort of met it before. I'm pretty sure that's true. Upstairs here, this is applying Newton's second law to the first mass. And downstairs here, this is applying Newton's second law to the second mass. So I'm just applying F equals ma. The acceleration of the first mass I've written as the second order differential of the position of the first mass. Curvature of this position, and similarly for the second mass, I've written its acceleration as this second order differential. I'm using this double dot notation on this slide. I randomly changed it. That acceleration is determined by the sum of the forces that are acting on the first mass will determine the acceleration of the first mass, and some of the forces acting on the second mass will determine the acceleration of the second mass. In both cases, there are two forces. So for the left-hand mass, you've got a force that arises from the left-hand spring that's attached to the wall, and whether it's stretched or compressed, and also from the right-hand spring, the coupling spring, whether it's either compressed or stretched. So I've written those two forces here using Hooke's law. So this P1 x1 is for the far left spring, so it involves its spring constant A1, and it just depends on the position of mass number 1, because that determines alone whether that's a stretched or compressed spring. For the force from the right-hand spring on mass number 1, so that's K2, that depends on where mass 1 and mass 2 are. It depends on that determines how much that spring is stretched. So it depends in this way. Similar argument, right, for the second mass, the right-hand mass. There's a force from the right-hand spring that only depends on the location of the right-hand mass. Here's the right-hand spring constant 3, and then there's a equal and opposite to the term in the mass 1 differential equation. There's a force from the coupling spring, so the K2 here, and of course that depends not on individually the positions of the two masses, but their relative separation to one another. I then rearranged this a little bit for convenience, rearranged it into two terms not corresponding to the two forces, but two terms corresponding to multiplying either the function x1 representing the position of the first mass or the function x2 representing the position of the second mass. So we get, these are our coupled differential equations. Look, the coupling's occurring. This first equation involves the differential of x1, but it contains the function x2. So that's the coupling. Lower equation contains the second order differential of x2, but it contains x1 in it. So that's the coupling there. This is a very useful approach for 2 masses in the 3 springs problem for the analytical solutions. And it's very especially useful because it's very extendable to supposing you had 3 masses and 4 springs, like you will have in the homework, or you had n masses and n plus 1 spring. It's just a procedure that's extendable to all those cases. So it's really quite nice and it's really quite neat. We're going to write the 2 coupled differential equations using linear algebra as a matrix equation. So I'm introducing vectors and matrices here. I'm going to make a vector out of a column vector out of the 2 position functions that we want to solve for, out of x1 and x2. That's my position vector. And I'm going to make 2 matrices. One's called the mass matrix because it involves the masses. One's called the stiffness matrix because it involves the spring constants. And this is the mass matrix, and this is the spring constant matrix. And this equation here involving these 3 things, this little matrix vector equation. So n is a matrix. This is a column vector. A is the stiffness matrix. Column vector again. This is representing this pair of equations here. So if you would have, the way to see this is to plug in the x, plug in the n, plug in the k into here. You would see that if you carry out the product of x double dot and x with the first row of the matrices m and k, that gives you the first equation. If you carry out the product of the x double dot and x with the second row of the matrices, then that gives you the second equation. This is the matrix form of this pair of equations. And by putting it in a matrix form, it's very easy to say, extend it, as I said, to 3 masses and 4 springs. You just, instead of having a 2 by 2 matrix and a 2-element vector, you'll have a 3 by 3 matrix with the same pan and a 3-element vector. You could have 4 masses, and it would be a 4 by 4 matrix with a 4-element position vector, so on and so forth. Okay. Well, we want to solve, this is just rewriting the differential equations. We wrote out a couple differential equations once based on Newton's second law. We rewrote the couple differential equations second time using a matrix and vector language. We want to solve the couple differential equations, and we're going to start by learning what we can and solving them analytically. So the typical path to solving them analytically, the typical insight you can get analytically, is to, let's first just guess a solution. Let's hypothesize a solution based on our experience with, say, a single mass on a spring and how we understand its motion, its sinusoidal motion, if we displace the spring. Let's guess that there's a solution to the coupled spring arrangement of 2 masses and 3 springs that involves the 2 masses, like a single mass, the 2 masses oscillating to and fro. Let's guess that there's a solution in which they oscillate to and fro with the same frequency. That's going to be my kind of answer, so my hypothesis, and we're going to try it out. Is there a solution of a couple, two masses, three springs, where we see the two masses oscillating with a common frequency? So we're going to try that out. So that's going to be my hypothesis. Here I just reproduce the matrix form of a couple of differential equations and the definitions. There's nothing new on this line. And here is what I just said in words. So I'm going to hypothesize, guess, that there's a solution to these coupled equations that is sinusoidal oscillation of the two masses with equal frequencies. And to write that as an equation, formula, a hypothesis, I'm going to, here's my, again, this is my vector x. It contains the two functions of time, x1 and x2 in the column here. I'm hypothesizing that these functions, x1 and x2, are oscillating, they're sinusoidal. I could write that as, you know, a sine omega theta. I could write it as a cosine omega theta. It's just handier for what we're going to do to write it in terms of an exponential with an imaginary exponent. So I've written the fact that I'm hypothesizing they have a common frequency by writing their time dependence as simply e to the I omega t. I'm not hypothesizing anything about the amplitude of their motion. So look, I've given the amplitude of the mass on the left its own amplitude A1, and mass on the right its own amplitude A2. And I'm also not hypothesizing, a little bit hidden here, anything about the phases of the oscillation. I'm going to let A1 and A2 complex numbers. If they were both just positive real numbers, they would be in phase. But if I allow them to be complex, the difference in their phase of these complex numbers would be the difference in the phase of the sinusoidal oscillation. So these are two numbers, but they're complex numbers. And so I'm allowing the phase to be different, the amplitudes to be different, but the frequencies to be common. That has clarified my kind of hypothesis, my answer. Okay. So that's just what I'm going to try out. So I'm going to plug that in. Take this idea from the last slide, plug it into this matrix representation of the couple of differential equations from the slide before that. When I plug it in, I'm going to carry out the second order differential of my hypothesis. The second order differential of my hypothesis, these are complex amplitudes, they're time independent, so they're going to stay the same. What I'm going to be differentiating with respect to time is just e to the I omega t. If I differentiate e to the I omega t twice for the second order differential, I'm just going to get e to the I omega t back with a factor of minus omega squared, multiplying it. And so that's this minus omega squared here. Then I can recognize that in my differential equation, I've got a common time-dependent term on the left and right. I can cancel those out. It leaves so that removes the time dependence. It leaves an equation that is a matrix vector equation, this one here, that relates, if you think about what's buried in that equation. Buried in that equation is the masses, the M1 and 2 are in the mass matrix. The spring constants, the K1, K2, K3 are in the stiffness matrix. Those are the kind of knowns in the problem. So it contains the knowns, the M's and the K's. Also contained in here are what is the frequency? What are the frequencies that this hypothetical solution obeys, where the masses are oscillating with the same frequency, maybe in phase, maybe out of phase with different amplitudes. What is that frequency? Well, that frequency omega is sitting in that equation. And what is the amplitude? What is the possible amplitude of the motion with a single common frequency? That's hidden in the A. So the knowns are in the K's and the M's, and the unknowns right now are in the omegas. There's the omega, and there's the amplitude, the A1 and A2 in this vector here. So we want to solve for those now. First thing I do is solve for the frequency. Once we solve for the frequency in terms of the spring constants and the masses, once you know what the frequency is, you can go back to that matrix vector equation, plug in that frequency, and you'll immediately see what the amplitudes are, what the relationship between the amplitudes A1 and A2. So the first step is really get the frequency. To get the frequency, at least one way of getting the frequency in this matrix vector language is to realize that our equation from the last slide downstairs here has the form that this product of the vector on the right, two-element vector here, with the 2x2 matrix. This is a two 2x2 matrices that combine together to make one 2x2 matrix. That product, interestingly, is 0. So we can use that fact to find, we're going to use that fact to find omega. Now, there's two ways that you can make the product of a matrix and a vector 0. If you got a symmetric matrix or a same type vector, right? 2x2 matrix, two-element vector. Two ways you can make that 0. There's a very trivial way you can make it 0, which is completely uninteresting to us. You could make the little a, you could make this vector here, that little a, you could make that 0. That immediately makes the product 0. But that's saying that you can fulfill the equation with 0 amplitudes for the oscillation. So it completely solves it. It's completely uninteresting. There's one other way. This vector could be non-zero, and this product be 0 for one particular type of matrix. Matrix where the determinant, with a determinant of 0. So if the determinant of this matrix is 0, and this is a result from linear algebra, if the determinant of that matrix is 0, then the product of the matrix and a non-zero vector can be equal to 0. And so we're looking to find omega from the solution of this equation. What I'm saying here is that you can find it from the solution to this, the interesting solution, non-trivial solution to this equation here, it can be obtained by setting the determinant of that matrix, I call it A here to be 0. If you want to remind yourself why is the determinant A equal to 0, the key to solving this. If the determinant of a matrix is 0, that means think of this 2x2 matrix. If the determinant of the matrix is 0, it means the two columns are linearly dependent on one another, proportional to one another, or the two rows are proportional to one another. Only if the two columns or the two rows are proportional to one another can it be that it can multiply the vector A and you get 0. It has to be that the two rows are proportional to one another. So this is the key point. So I'm going to, for the purpose of solving it, just to keep the algebra down, let's imagine the special case where the masses are the same masses. Let's imagine the special case where the spring constants are the same spring constants. So I've just got a mass M. I've just got spring constant K. Let's fill that into the determinant of that matrix. This is the matrix whose determinant has to be 0. So if I fill in the values of M and K into this difference between the stiffness matrix and the mass matrix, where the mass matrix is weighted by omega squared, the unknown that we're trying to figure out, I get this little equation here, this determinant here. This has got to be 0. If I multiply this determinant out, the top left corner times the bottom right, the top right and the bottom left. That's this little guy here, which I can rearrange in this form here, which tells me that the values of omega that fulfill this equation. There are 2 solutions, one corresponding to the first term in parentheses, the second one, the second term in parentheses. And these two solutions are that omega, I call it omega 1 here to differentiate it, is the square root of k over m. Or that omega, call it omega 2, second mode, is the square root of 3k over m. So these are the 2 frequencies that are allowed for these common frequency oscillations of the 2 masses. So at this point, we've learned that our hypothesis, or I guess, that there is a solution that involves common frequency of oscillations of the 2 masses. That hypothesis, that guess, is fulfilled. There are 2 solutions, and there are 2 kind of distinct solutions that we call the normal modes that have frequencies that are determined by the values of the springs and by the values of the masses. They are these 2 frequencies here that are labeled omega 1 and omega 2. So we found the frequencies now. Out of that great ocean of frequencies, right, of any possible frequency, these 2 masses on these 3 springs can only oscillate in common frequency with these 2 very special frequencies, these 2 normal modes. Okay. We didn't yet solve for the amplitude. And if we want to picture the solution, we want to solve for the amplitudes of the oscillations. But once you've got the frequency of the oscillations, and if you remember that product of the matrix and the vector is 0, once you've got that omega, you can plug that omega, which is a function of k and m, you can plug that omega into the matrix, and you can solve for the relationship between the amplitudes. So that's what I'm doing on this slide for the lower frequency, the one that's the square root of k over m, the smaller frequency. It's the longer period. For that frequency, I plugged that frequency in this omega squared here. For omega squared, I'm replacing it with k over m. If you replace omega with k over m, that difference between the stiffness matrix and the mass matrix becomes just this little guy here. Very little compact symmetric matrix involving the spring constant. With the spring constant size on every element, and the diagonals is positive and the off diagonals is negative. You can immediately see from that what values of A1 and A2 are allowed. Well, what it restricts it is the equation restricts A1 and A2 to be is that A1 and A2 must be the same. They must, and remember they're complex numbers, so they must be same in size and they must be same in phase. So what we've just learned is this solution, the lower frequency solution, where the 2 masses are oscillating at the same frequency, they're oscillating also with the same amplitude, and they're also oscillating with the same phase. When one moves towards the right, the other moves towards the right, and so forth. And so here's a picture of that solution that doesn't tell you much, but amplitude, the overall amplitude, you're still free to pick based on initial conditions, but the amplitudes of the 2 motions are the 2 masses are the same. They are in phase, and they have this particular frequency determined by the spring constant and the mass. So that's one solution. There was a second mode that we discovered. It was the higher frequency mode, It's a higher frequency by a factor of square root of 3. And we can take that frequency and plug it in also to that matrix vector equation, replacing omega squared by 3k over m, and see what that tells us about the amplitudes of the oscillations when you have that mode, that particular frequency, the higher frequency. So that's what I did here. Here's my linear equation again. I'm going to replace the omega squared with the particular frequency for this mode. So I'm replacing it now with, there's a typo here, so it should be a 3. I want to plug in 3k over m for omega squared. And if you plug in 3k over m, you also get a really simple matrix. Same size on each of the 4 elements of the matrix, always k, and they're all the same sign also. They're all k, and k. So that's the matrix that emerges, and then you can see immediately, well, what values of A1 and A2 would fulfill that equation where the matrix with all those elements k in it is multiplied by the vector of A1 and A2. Well, it's fulfilled if A1 equals minus A2, if they're equal and opposite. Meaning both their sizes are the same, but their phases are opposite. So if A1 is positive, then A2 must have the same size and be negative. That's an opposite phase. But you could also have, A1 being positive imaginary and A2 being negative imaginary. Anyway, so we just learned that A1 must be the opposite side of A2, i.e. there's some overall amplitude that's going to be set by your initial conditions, but the sizes of the oscillations of the 2 masses are the same, but now they're out of phase with one another. When one's going to the left, the other one's going to the right, and vice versa. And so here's a picture of that. Not very instructive, but these 2 oscillations have the same amplitudes, have the same frequencies, but they're completely out of phase with one. Okay, so that's what we can basically learn from analytically solving the problem. We've learned that we should, if we explore the problem numerically, we should be able to see these 2 modes, 2 normal frequencies, where the oscillations are either in phase with one another in the same amplitude or out of phase with one another for the same amplitude. We should be able to find those, but of course we should be able to find all sorts of other solutions that are much harder to explore numerically, much harder to explore analytically. Okay. There's a typo. There's 2 typos on the slide. This is a typo. It's out of phase. These are cut and paste typos. This is a 3. Okay. Let me go to the code. So here's my code. In my code, I've made user function for, we're going to use the same sort of, let me step back. We use the same sort of procedure that we used earlier on for solving an ordinary differential equation, except now we're going to be solving a couple of differential equations. When we solved an ordinary differential equation in the past, we started with the Euler method for solving the differential equation, and we looked at ways of improving the Euler method using higher order of Taylor approximation. We looked at Runge-Kutta methods, and especially Runge-Kutta. In this example, I'm going to use the Euler method. It's one way of solving the numerically the coupled differential equation. So I've got a function here in Euler that takes the positions and velocities of the masses at a current time step, and it's going to propagate them into the future at the next time step. And then down below, I've got a second function that I'm going to talk about, which is a little bit more sophisticated function for propagating the current positions and velocities of the two masses to the future positions and velocities of the two masses. So one of these we've met before, Euler method. It's the simplest approach for propagating positions and velocities to the next time step. One of them is a little bit more sophisticated approach that addresses a particular problem of the Euler method for oscillatory differential equations. And we're going to talk about that when we get to it. But for now, just imagine that I define these two functions. I call this one dkd. This one isn't Runge-Kutta. This one isn't Euler. It's sort of an extension of Euler to what is called drift, kick, drift. And you see what drift, kick, drift means when we start walking through this bit of code. But for now, I think I'm going to not describe that one, but rather move on to the body of the code. We'll see how it works with the Euler method, and then we'll go back to the new method, the drift, kick, drift method. Okay. So we've got a function, but for the moment, just imagine we've got to use a function that would take the position velocity coordinates from the current time to the next time with this little time increment. This is the Euler method, and we've already in the past written this and used this function many times. Of course, you have to write it specific to your particular differential equation, which in our case is a pair of coupled differential equations involving 3 springs attached to two masses. But the Euler method we've used multiple times for falling bodies, for projectile motions, for masses on springs, for pendulums. So here I'm setting up a bunch of parameters that I need. The masses of the two masses, M1 and M2. I'm going to, I think, just work in this world where they're equal masses. That'll keep things simple. The spring constants. We've got 3 spring constants. I'm going to mainly work in a world where we'll look at the case of when the spring constants are all equal. But I'll also vary the coupling spring strength. So I might actually make it the spring constant 0, which is as if the spring isn't there. And we can explore that because that switches off the coupling. And that might be interesting limit. I can also make it small compared to the other spring constants. So there's what's called a weak coupling between the two springs. And that's an interesting world to explore, the weak coupling, and so forth. So I'm not going to explore the whole space of K1 and K2 and K3. I'm going to keep K1 and K3 the same. But I will explore K2, turning it on, turning it off, changing the sign. The normal modes, those normal mode equations applied, remember to find the normal mode equations, we had to plug in the fact that K1, K2, K3 are all the same, M1, M2, they're the same. Then we got the two normal mode equations. So I'm going to print out the normal mode frequencies and periods. But remember, this only applies if you've got equal masses and equal spring constant. If you don't have equal masses and equal spring constant, we haven't addressed that solution. And that's the nice thing about numerical solutions, is just as easy to address that solution. Okay, so let's print out the normal modes. We can check that against analytical solutions that we record. Then I've got to define initial conditions, of course. Initial conditions here are the mass and the velocity initially for mass number 1 and the mass velocity initially for mass number 2. So I've got these initial conditions here. I'm typically going to vary, I laid them out this way because mostly I'm going to vary the positions. And I'll just imagine I'm releasing the masses from rest to just keep things simple. So we're gonna do that. Downstairs here, well, look, the whole process works on discretizing time. So I've got to discretize time. I've got to define the increments of time that I'm going to use. I've got to define the range of time that I'm going to use. And so these three quantities are defining that. dt is the increment. Look, I've set it as a millisecond. The time range is from 0 to 200 seconds. And so I've got 200,000 time increments that I'm going to walk through when I do my calculation. We want to look at the motion as a function of time. We want to plot the motion as a function of time. We want to explore x1, x2 as a function of time. So I'm initializing some lists that are going to accumulate the proxies for the independent variable, dependent variable for time and x1 and x2. When I initialize them here, I actually initialize them with the first element of the list, which is from these initial conditions. Okay. As usual, it seems the actual calculation of x1 as a function of time, x2 as a function of time, is a very compact part of the code. It's just for the Euler method, which I'm going to use here, is calling this one function. Inside this loop, which continually loops, incrementing the time increments until the maximum time. It was just going to walk us through the 200,000 1 millisecond time step that there are over a 200-second period. And each time I go through, I'm going to increment the positions and the velocities of the two masses. The Euler function, you'd have to remember a long way back to the arguments with the Euler function. The arguments of my Euler function here are, I'm going to pass the, of course I need to know the time step, how far forward I want the Euler function to take us. I need to know the current positions and velocities of the two masses, so I'm passing those. That's x1, x2, v1, v2. I need to know, the parameters of the system. So here I'm passing through to the user function the masses and the spring constants, the two masses and the spring constants, just to make it explicit what the Euler step will depend on. And then it's going to, having passed all those arguments, it's going to return the positions and velocities of the masses at the future time. I'll store the new positions and new velocities. I'll store the new positions. Sorry. I'll store the new positions in the position list here, along with the time in this time list here. So this is where I build up my proxies for independent and dependent observables. And then I'm just going to do some plotting. So that's the format of the code. Let me just go back up to the Euler function so we know exactly what it's doing. Now we've seen how it's called. Each step I call it. What's it do? Calculates the acceleration of the two masses based on the forces acting on the two masses, so based on second law. and that those forces are coming from the springs, the compression or extension of the springs, and based on those two equations, the first two equations that we wrote down on my little sequence of slides. So that's this A1 and A2. It's just on the slides, it was X double dot 1, X double dot 2. So that calculates the acceleration. I use these accelerations and the current velocities to project to the current positions and velocities at the end of this step in time delta t. So then I calculate the new positions based on the current velocity, the time interval that I'm projecting for, and current position, and I'm calculating the future velocity based on the current velocity, the acceleration I just calculated, and the time interval. So this is classic Euler method for taking what you know at the beginning of the time step. I know my position, I know my velocity, I just figured my acceleration. Well, I'll just say that that goes on to the end of the time step and I just project forward. Okay, let me run it. After doing all the calculations, I make 4 plots, and I won't go through the plotting code, but I will describe the plots. Okay, four plots. What are the 4 plots? The 4 plots that I'm going to show you are those are the position of mass number 1, so it's x1 as a function of time for the 200 seconds. The horizontal axis is time, and the vertical axis is the position of mass number 1. So that's the red graph in all my plots. Green graph is the same thing, but for mass number 2. The position of mass number 2 as a function of time for the 200 seconds. What about the 2 lower plots? The 2 lower plots are to think of them as the average position of the 2 masses versus time. I actually just summed x1 and x2, but if I divide it by 2, it would be like the position of the center of mass versus time. So that's the gray one on the left-hand side. Think of that as the position of the center of mass as a function of time. And the one on the right-hand side, that's the difference in x1 and x2 as a function of time. This is the one that would tell us whether we're kind of stretching or compressing the spring in between the two. So the x1 and x2 are pairs, but it's also interesting, going to be interesting to look at the sum of x1 and x2 and the difference in x1 and x2 on these 2 lower plots. Now, what did I run this with? And let's go back upstairs and run it with a few test cases. So let me first just switch off the coupling spring. I've set K2 to be 0. So there's no coupling between the 2 springs on connected springs now. And let me just start with, well, as it is here, displacing the mass on the left, but not touching the mass on the right. What would we expect in this situation? If I have effectively removed the coupling between the 2 masses, the one on the left, if I displace it and release it, is going to vibrate at its natural frequency. The one on the right is going to sit there. So this is an important test case. If we run that, that's exactly what we see here. Here's the mass on the left-hand side, oscillating to and fro. This is the one that we displaced. Here's the mass on the right. It's not moving because there's no coupling. These plots aren't very interesting in this case. If I was to add these two together, I just get another plot of x1 moving, another plot of x1 moving. So not much interest there. Okay, but that at least says that we get a sensible result if we switch off the coupling. Let's switch on the coupling. Where is that? Here. Switch on the coupling. And here we go. This is the case we solved analytically now. Equal masses equal spring constant. And I'm going to displace both masses. By an equal amount towards the right. And then I'm going to release them. So this is, I'm releasing the masses displaced kind of in phase with one another and with the same amplitude as one another. This is exactly the circumstances of the lower frequency of our normal modes. In the lower frequency of our normal modes, the two masses are in phase with one another with the same amplitude. So here I'm starting with them with the conditions of being in phase with the same amplitude. Let's see what we get here. Mass on the left is oscillating. Mass on the right now is oscillating. All three springs are active here. What can we say about their frequencies? Well, their frequencies look to be the same. The period is about 6. The 2 pi, the way I set it up is 2 pi seconds. A little over 6 seconds. They're both 6 seconds, so they have the same frequencies. And also, if you look, they're in phase. These oscillations are in phase. If you look at time 0, we start in phase with the red and the green curve, and they stay in phase, and they end in phase with one another. So this is exactly the lower frequency normal mode. The two masses are oscillating to and fro. They're oscillating with a common frequency. They're oscillating with a common amplitude, and they're in phase with one another. That's the classic normal mode. Another way of seeing it's very clear is to look at these lower plots. In the normal mode with the lower frequency, the masses are kind of swinging like this, to and fro. The separation between the masses is found the same. They have the same amplitude, they're in phase, so the separation between the two masses is the same. So the difference in x1 and x2 is 0. And this clearly shows you've got in phase oscillations of the two masses with same amplitude. Oscillation of the two masses. Okay. I am going to change the initial condition. I'm just going to put in that minus sign. So now I'm going to start the two masses with the same amplitudes again, but I'm going to start them exactly out of phase. One is over to the left, and the other one's over to the right. I'm going to release them. This is exactly the conditions of the second normal mode, the high frequency normal mode. It had the two masses oscillating with the same amplitude, with the same frequency, but being out of phase, 180 degrees, pi out of phase. So I'm recreating that condition in the initial conditions here, with the two amplitudes being equal and opposite. So let's release this one, anticipating that we'll see the other normal mode. And here's the result. This is the oscillation of the mass on the left, oscillation of the mass on the right. This frequency, I don't know if you remember what the frequency looked like in the last plot, but this is a higher frequency, right? We see more oscillations, yes.
Is it so easy?
Yes, fantastic. We're going to show, can I finish this little discussion? And then I was going to pose the question, anything off? We already seen that on this one, there is something off, actually. And it was on the previous one. It was increasing a little bit, but it's increasing more obviously on this one. So you are using the Euler method. Right? So we'll come to that in a moment, but that's a great point. So this is a key point that we're going to come to. But for the moment, let me just say that we are seeing the higher frequency of the higher frequency normal mode. We are seeing them oscillate with the same amplitude, same amplitude on the left and right. We are also seeing them oscillating very clearly 180 degrees out of phase, right? If they're oscillating 180 degrees out of phase, they're kind of doing this. One's going to the left and one's going to the right. Their average position, if you do this, what's the average position of my hands as I do this? It's just right in the middle, standing. This is their average position, or their sum position. It's dead zero. So they are literally 180 degrees high out of phase. All the oscillations are in the relative motion. So if we plot the relative motion, that's swinging with an amplitude of twice the individual amplitude, plus or minus 2 centimeters, rather than plus or minus 1 centimeters, because they're 180 degrees out of phase. And so that's what we see here. So we've reproduced all those features of the normal modes that we explored, encountered, understood with the analytical solution. But of course, look, the great power here is that I could launch these masses with any amplitudes or velocities I like. I could launch these masses with any values of the spring constants or masses that I like. And so this numerical method is very amenable to solving all sorts of problems that are difficult. Now, let's come to your question. On this plot, there's a problem, right? The amplitude is growing. Now, is that reasonable? Well, look, the amplitude is going to grow. The energy stored as kinetic and potential energy, or the springs and the motion, that is a reflection of that must be growing. And it is nothing in my problem to make the energy grow. The energy should be conserved quantity. So there is a problem. It was in the previous solutions too. If I go back and change that minus sign, this was the solution for the lower frequency normal mode. You can see it also has a slope to it. It's a slope that accumulates over each oscillation. So we saw it more in the higher frequency case with more oscillations. It accumulated less in the lower frequency mode with the lower operations. It stood a problem of the Euler method when applied to, especially when applied to problems where there's oscillatory motion. So the Euler method does not conserve energy, and it does not conserve energy at the order of delta t, the time step. It's an order delta t problem in the Euler method. It's not conserving the sum of the kinetic energy determined by the velocity v and the potential energy determined by the positions x1 and x2. You can compute the sum of those kinetic and potential energies. It's not conserving that. That would be okay if sometimes it gained energy and sometimes it lost energy on each step, right? If it's just inaccurate in a way that sometimes went one way or the other way, maybe that's just noise. But unfortunately, the Euler method always fails to conserve it in the same direction. So in that case, it's always every step is not conserving the energy, and it's also not conserving the energy in a way that increases the energy. And so it accumulates energy non-conservation over these many oscillations, and that's what we see. A common fix for that is a little more sophisticated method than the Euler method. It's a different method from the Runge-Kutta method. It's a method that was specifically developed for the type of problem where you have to enforce energy conservation. So it enforces energy conservation. It enforces it. There's only energy non-conservation in the method I'll show you at order delta T squared, but also the energy non-conservations that occur at delta T squared don't accumulate. So it does way better with energy non-conservation. So that takes me to this other user function here. So I'll try and explain this function. Firstly, the arguments of the function are exactly the same as the Euler method. Just passing the same information. The return of the function, exactly the same return as the Euler method. It's getting the current positions and velocities and reporting back with the new positions and velocities based on being past the time interval, delta t, that we want to step forward. It does it by a drift hit drift method. And what the Euler method is doing is taking the acceleration computed at the beginning of this step at the current time, taking the velocities known at the current time, and then just applying those. It's just giving one big kick forward to the later time, delta t later. You know, if the positions and the velocities are going to, if the positions and the accelerations are going to change over that period, that time interval delta t, it's going to make a mistake because it's just taking what they are currently now and assuming, assuming they're just going to stay the same over this period delta t. So drift tries to do better by, firstly, it just drifts the particle forward by half of the tick, half of the increment. So that's what this calculation is here. We're going to calculate the new positions of the particle after drifting for. Am I on the right one? Yeah, drifting to not drifting for delta t, but drifting for just half delta t. I have not touched the particle yet, or the mass yet. I've left its acceleration velocity as they are. And I just let it drift to the middle of it. And when I get to the middle of the tick, I calculate the acceleration at the middle of the tick. That's these formulas here. So they're exactly the same formulas as the Euler method, but now it's this new position at the middle of the tick. At the middle of the tick, then I use these to change the velocity. Here's the acceleration. I use these formulas to change then to drift the remaining half of the tick width to the end of the tick. So here's a second drift to the end of the tick. So stand back from this and think of this little plot is drifting the particle, changing its position to the middle of the tick. Then I compute the acceleration, kick it. Here's where it accelerates, changing its velocity at the center of the tick. And then I drift it the remaining half to the end of it. So this is why it's here's drift, here's kick, and here's drift. And I'm not proving this in any way, but this drift method gets rid of the problem of the delta T order energy conservation, and leaves behind just a delta T squared energy conservation problem that doesn't always add in the same direction. And so we're going to use this, and this should help us. So to implement that, I'm just going to comment this in, comment that out, and then rerun. Where am I? This is the lower frequency normal mode. And I would say now that I don't see any energy non-conservation by eye. By this amplitude, with the mass on the left, the amplitude of the mass on the right, and those stay the same. We could also try the higher frequency mode. And again, what was a really obvious energy non-conservation, at least by eye here, there's no obvious energy conservation. The amplitudes are staying the same. So this is this drift algorithm, which is pretty simple, right? As I say, just drift to the center of the tip, hit it there by estimating the acceleration there, and then drift to the end of the tip. Just a simple, slightly more complicated version of Euler method solves the energy conservation problem, and it's used a lot. So if you were an astronomer and you were looking at the motion of astronomical objects, I don't know, planet in the solar system, this is really important to you. You don't start not conserving energy. Because if you're going to follow that planet and it keeps spiraling out and out because you're not conserving energy with the Euler method, that's going to be a problem. So this is commonly used in that type of differential equation problem where you've got something oscillating, something orbiting like a planet around the sun. Just show a couple more cases. Let's make this a weak coupling spring in the middle. So it's not the same strength. It's just a weak strength compared to the springs that are attached to the wall. And let's see what happens if I make that one change. Let's see if what happens if I displace the mass on the left, but not the mass on the right. So we already tried this situation where the coupling spring is zero, and the spring on the left-hand side just oscillated freely, and the spring on the right, which was uncoupled, didn't move. What about if I introduce a little bit of coupling? We get these interesting plots here. This is how we're starting this arrangement with the weak coupling central spring. I start with an amplitude of 1. We start with 0 amplitude for the second mass on the left. One is displaced on the right, the red plot on the left. One is it's not displaced on the right, the green plot. We see that with time, through the coupling between the two masses, the amplitude of oscillations of the mass on the left that we initially displaced die off and actually vanish with some some point here. And in that time interval, the oscillations, the one on the right, are increasing with time, and they're maximum at that time. You can see here the flow of energy, right? We started off with all the kinetic and potential energy in the mass on the left-hand side. We only displaced it. That energy with time flowed to the mass on the right-hand side, and at this moment of about, I don't know, 30 seconds. The energy is all in the mass on the right-hand side. But now this is like a symmetric situation. Now we've got a moment where the mass on the right is oscillating and the mass on the left is stationary. We're going to just have that energy flow backwards into the mass on the left, into the kinetic energy of the mass on the right. So we see this beating, and this beating is the flow of energy to and fro between these two beating oscillators that are weakly coupled to one another. And the beat frequency is another frequency that's introduced here. And the beat frequency and the oscillation frequencies are related to the average and difference between the determined by the average of the distance and the difference of the frequencies corresponding to the two spring constants we got here. We got a strong spring and a weak spring. A K over M would give us a high frequency and a low frequency, and those determine these beat frequencies.